to introduce our next speaker, Professor John Fernandez. Professor John Fernandez has been a faculty member of MIT since 1999, and he is the founder and director of the Urban Metabolism Group, which is a multidisciplinary research group focusing on the resource intensity of cities and the design and technology pathways for future urbanization. In addition, John Fernandez leads the Environmental Solutions Initiative at MIT, and this initiative is MIT's institute-wide effort to mobilize the scientific, engineering, policy, and design capacity of our community to contribute to addressing climate change and environmental challenges of global import. Welcome, John Fernandez.
Thank you very much. Okay. Okay, first of all, thank you for the invitation, and apologies for not being here this morning and having to leave after my presentation. I'm actually going to another event. I'm going to be talking about the Plastics and the Environment program that the Environmental Solutions Initiative has started. It is still young. We are essentially in our second year, so it is evolving, but it's expanding pretty rapidly. Before I do that, I want to talk about what the Environmental Solutions Initiative is at MIT. So 5 slides on that, just so you're well aware. So along with the other initiatives, like the Energy Initiative and Open Learning, the Environmental Solutions Initiative is meant to mobilize the MIT faculty in addressing the most challenging, the most vexing environmental issues that we have, appropriate to our capacity and our interests. So we're not just interested in any old environmental issues. We're actually interested in those that we can really shift the needle on, move the needle on. So, you know, as mission statements go, this is ours. We are 5 school. We are across the entire institute. The things that we do would be the things that you would expect. We have a research program that's comprised of research seed grants in areas that I'll talk about in a second. We also manage an environment and sustainability minor for all undergraduates. So how does that relate to plastics? Well, for example, we have a professor introducing the challenges to recycling in one of the STEM classes that undergraduates take here at MIT. So I'm going to talk mostly about the solutions on the research side, but I also want to make sure I just mention the idea that it's really important to make aware and mobilize our students, because plastics is not going to go away. The plastics pollution problem is not going to go away with our research or within 10 years. It's here to stay for some time and may get much worse, as you'll see in a moment. We're also involved in engagement, bringing people to campus, engaging with partners on environmental challenges. So a super quick synopsis of what we cover is that after about a year of having discussions, my first year as director, we settled on these 3 domain areas. So climate science and earth systems, cities and infrastructure, and sustainable production and consumption. Sustainable production and consumption, sometimes we use the shorthand of circular economy. These 3 areas have many subtopics, and the measure for us of the inclusion of a subtopic in our scope is there a professor or 2 or 3, is there a research lab interested in that subtopic? If you're interested in the fuller picture of our research agenda, please go to our website, environmentalsolutions.mit.edu. You'll see we have a research agenda, and it goes into a lot of detail on what we do. Some texture to the kinds of research that we support. Next generation models, so machine learning for climate models, better metrics for a full range of greenhouse gases and the radiative forcing that accompanies them, a circular economy project on repurposing industrial waste for for purposes that have not been identified yet. We're also into transportation, but as you might know, there are other groups at MIT doing environmental work, and we are always asking ourselves the question, are we adding value to the inclusion of a topic? Are we filling a gap? Are we complementing other groups like JWAFs, for example? Deep sea mining, the incredibly important and difficult issue of what are the ecological consequences of deep sea mining, which is about to start to happen in a huge way in the Pacific. So the professor here, Tom Peacock in mechanical engineering, likes to say that this is the first anthropogenic, large-scale anthropogenic extraction activity, new one, novel one, that is now going to be preceded by an ecological study, never before in human history. And hopefully, he's very connected to the law of the sea. Hopefully some of that work will inform the regulation before there's widespread ecological damage. And then we also engage in climate communications, information going out from MIT, but then also engaging with partners on the discourse on climate change. Okay, so that was it for the ESI. You know, I give presentations on the ESI that last an hour and a half. So there's a lot more to say, and please do visit our website. You'll see a number of things that I didn't mention. Okay, so one of the ways in which we support research is to ask what are the key questions that MIT might have some capacity in addressing. And we arrived at plastics about a couple of years ago. We started to bat around the idea, talk to faculty, and decided what we would do is explore launching in this area. It's, I think, helpful to say that from my perspective, plastics in the environment is one of these charismatic environmental topics. You know, there's a lot of interest in it. Lots of groups are jumping on board. And not to sound too presumptuous, but I think a lot of work is not really going to do much in the plastic pollution issue. And to begin with, until we stem the source, good luck cleaning up and everything else. You know, until we stem the source, it's like carbon emissions. Until you mitigate, good luck, you know, taking carbon out of the atmosphere and all that sort of stuff, planting more trees. So that's really the key concept here. And so we wanted to really address that in the way that MIT and you know, when I say MIT unique, I'm not just being partisan to MIT. I'm saying that there are professors who are here at MIT who aren't elsewhere. And they have very particular tools, and I'm going to talk about a few of them. So that was the idea to begin with. And again, I apologize if you've seen this. But have you seen this? Plastics flow globally? No? Okay. So a little bit of so you haven't at all, really? Interesting. Okay, so good. There's very little knowledge about the extent, the volume, and the geographical extent and the volume of plastic pollution. One of the key papers is Roland Geyer, 2017. He's an industrial ecologist, and this is the cumulative. This is the total amount of plastics that have been produced. I'm not going to go through these in detail. You can take a look. They're self-explanatory. Another data point to keep in mind is, you know, around 1989, the volume of plastics exceeded the volume of steel production. Okay, that's all very sort of sobering and daunting, but we've just begun. We're really at the beginning of. This is the cumulative. This is actually up to 400 million metric tons of annual plastic production. And the cumulative plastic production, again, the figure in the previous slide was something like 8,000 million metric tons. So we're somewhere around here or so. 28% of the projected plastic production by 2050. So let's say a third. So 2/3 is yet to come. So that's why I was really emphasizing, until we stem that source, you've got imagine a bulk of 2/3 of plastics coming, and what are we going to do about that? It's important to also mention that the center of gravity of the production, the geographic center, is not, well, understandably, and maybe needless to say to you, shifted to Asia between 2006, 2014. China's gone from 21 to 26. we've gone down, Europe has gone down, rest of Asia has gone up. And so that will continue to be the case. So we're, as in so many environmental topics that we're engaged in the States, domestic issues and the environmental, but the fact is the focus, or a major part of our focus, really does need to be international. And we need to collaborate with international partners in this problem. So the goal, so when I say stem the source, that's not the only thing we need to do. There's also, so plastics will enter into the economy, will not be attended to, managed well. And we have to think about how we're going to close material loops. And so the notion of the circular economy is relevant here. And the Ellen MacArthur Foundation has done a lot of work, circular economy and plastics, and they have a good plastics report. But the reality is this. It's quite messy and it's quite leaky. So the 400 million metric tons that I talked about, 75% becomes waste within 1 year, right? So that 75% then is dispersed in different way, and there's a significant amount of environmental release. So this graph, this diagram, produced by a postdoc working for Professor Desiree Plata in civil and environmental engineering, was really cobbled together from a lot of different data sources. And as you can see, there's a lot of uncertainty in this. So there really does need to be, a lot more work needs to be done for us to really get a sense of the problem as we're working on the problem. And I want to give full credit. So Brad Olson, Desiree Plata, Jeremiah Johnson, and the postdoc. Okay, so this is unpublished, but at some point it will be. And this is to build upon the Roland Geyer paper. So we decided that it was worthwhile exploring. So about a year and a half ago, we held a plastics workshop. We brought industry together with faculty, together with students and other researchers, NGOs, foundations, and the Rosalio Project was there and others. And we essentially did the hard work of trying to precipitate out of conversations areas that were relevant to MIT, in which we have capacity, in which we really, really feel like within 5-10 years, I don't want to be 80 years old before we, but within that amount of time, we've got some tractable solutions that either are commercialized, deployed in another way, somehow. So it's very ambitious, and along with that ambition came the reality check of what we can do. So we focused in on microplastics and microfibers as a particularly difficult problem, a wicked problem, because of the life cycle of microplastics, microparticle production, and the variety of sources, the dozens of sources of microparticles and microfibers, because they are derivatives of sometimes a bulk plastic, sometimes a process, many, many, many different sources. Everything from fishing to urban wastewater treatment plants. And what we ended up doing is articulating a domain space for the work that we're going to do. So I'm going to show you this, and then I'm going to talk about 2 projects that are part of this work. So the 3 areas that were clearly of interest and for which we had existing tools and maybe even the development of new tools, and there were interesting actual research questions, knowledge creation questions, were in the polymer engineering area. So tuned degradation. So first of all, the mechanics, the chemistry, the environmental science of degradation, and then understanding that really, really well to be able to control it better. Environmental sensing, so the fact that we know very little about where plastics actually settle. So we know the source, we have very little information about how they're dispersed and what the extent of dispersion is, but then where they settle, the fate of microplastics and microfibers. Environmental sensing, actually going out into the field and sensing and getting a sense of where they are, what it is, how much there is. And then environmental modeling, the idea of being able to then, with some of that information and with other kinds of information, model the actual dispersion of and the extent of that plastic pollution in waterways to begin with. Eventually, aerial dispersion of microfibers and microplastics we're also interested in. So these three areas were the first and I will talk about a project in polymer engineering and a project in environmental modeling. We did also scope out other areas, and I'll talk about these after I talk about those two projects, human health and ecology and reuse and recycling, which we renamed, and you'll see my rename in a bit. And then possibly product engineering, although I must say here at MIT, there wasn't actually a constituency, a faculty constituency for engineering products in a way that the final result was you had less plastic pollution. It's an important area, really important area. We just might not do it. So, and then something that we are very, very engaged in, and I'll tell you about a symposium, a workshop that we're having soon, but with partners, public policy and economic incentives, some good expertise here at MIT, but probably a lot of great expertise beyond MIT. Okay, let me talk about these two. So to begin with, so one principle of having an initiative be successful here at MIT, an initiative that is able to address the important questions apart from tenure track, apart from department responsibilities, apart from the academic context in which all faculty live and breathe, is a interested coalition of faculty, a cohort, an intellectual cohort that are really interested in being part of that group. That is maybe the greatest effort that we've made to develop that cohort. So obviously, with money, it's easier to develop a cohort, right? But also, with money and not an interesting intellectual question, you're not going to be able to develop a cohort. So it also has to be that really interesting, really important needle-shifting question. So we have a great group of faculty. I will talk about Desiree Plata's work. I'll talk about Tom Peacock and Pierre Lemerzieux's work, but we also are engaging with others in a whole variety of ways. And I don't have time to go into the rest of it, but really looking forward to pushing this forward. Okay, so Professor Desiree Plata, she's been at MIT for 4 years or so. Her primary objective, and I've read, I think, all of her publications, her primary objective is to use her career to embed environmental performance in the engineering and the invention of materials, products, services, everything else. That it's not an afterthought. That the performance functions of a thing are not the mechanical, thermal, electrical, dielectrical, whatever, are not more important than the environmental performance. That's not the way the world works today. All right, so it's really, really important for me to mention this because her work is all about understanding how much more do we need to know about the environmental consequences of new materials and products and services, and then how do you actually use that knowledge to design better so that we're not creating more problems with the new polymers and other materials. So the challenge here for her in specific is understanding the necessity of environmental degradability as a design metric. Degradability is often not captured holistically. Biodegradation includes biological, chemical, and usually this third is the one that's not appropriately represented. The mechanical aspects of degradation in a complex environment, at the seashore, in the deep ocean, in a wastewater treatment plant. You know, what are the mechanical actions on bulk plastic, on a film, on a fiber, on an apparel fiber that then creates that microfiber and microparticle. So she's now focusing on, I mean, it may not seem like super sexy to this audience, but on the standards for understanding degradation. So the OECD and other standards that are used to actually understand and then to label biodegradability. From her point of view, most plastics are woefully, are not biodegradable given the tests that we use today. there's more biodegradability in polymers and plastics if you include a fair representation of those three mechanisms for biodegradability. So the kind of tests that are used in water with an inoculum, either sewage or soil, in a tube over a certain amount of time, really does not lead, it's unsuitable for insoluble particles and films. Size and density are uncontrolled. And again, the marine microbial inoculum, of which there are still discoveries being made, right? We don't actually have a full understanding of the ecological richness of some of the environments in which plastics find themselves. And then the timescales and endpoints, almost all solid polymers, as I said before, would be non-biodegradable under this regime. So she has a history, she has a previous work in developing automated tests for very fast throughput of environmental testing of materials, because the challenge that she in her field faces is that the invention of new compounds, materials, new polymers happens much, much, much faster than the understanding of the environmental consequences of those materials. So it's got to be a much better automated and including artificial intelligence motivated or driven process for understanding degradability. So the work is ongoing. As I said, this project is about maybe a year and a few months old. The long-term vision for her is, as I started this section, an a priori prediction of environmental and material performance in the development of that material. So, obviously we have a good amount of information about a lot of compounds, but then being able to script those compounds in a way that you can then use artificial intelligence, and this is along with Brad Olson and Tommy Giacola, Regina Barzilay had some of this work, to be able to code the novel formulations into an AI language that can then be used to better predict the biodegradability properties of new materials. So this is a kind of a pretty abstract, fairly narrow niche for the work that we have engaged in, but it's absolutely fundamental, and it will be the anchor for a lot of other work in material production, polymer invention. It's always a little tricky to talk about other people's work. I mean, I'm always a little hesitant. It would be much better if Desiree Plata, she's much more charismatic and much better at presenting her own work as she would be. But I'm hoping that's a fair representation. So the other project I want to mention is on the modeling side. So, as I said before, the sources of plastics that then lead to microfibers, microplastics from urban wastewater treatment plants to fishing activities and other ocean activities, and dozens of others. So this is the work of Pierre Lemercier and company. A little aside here is that we actually supported Tom and Pierre with one of our seed grants a couple of years ago in the work on seabed mining, as I mentioned. So a portion of the methodologies and the partial differential equation modeling that they're using to understand when you're mining the seabed and you're taking those mine tailings to the ship and then you're dispersing them, what happens to those particles? How far do they go? What is geographic extent, both horizontally and vertically? What's the effect on the water column ecology? And then also, where are they deposited? So microplastics is just another kind of particle, right? And the source, so the fundamental methods that are being used, applied mathematical and obviously / computational methods are being applied to this. So modeling of marine plastics from the methodology, the partial differential equations, to actually informing optimal cleanup. So cleanup is happening today. More power to Boyan Slot, right? More power to him. But he needs a whole lot more information. He needs a whole lot more understanding of where is it coming from and how long after you clean up that partial bit of patch, how long will it take for that patch to rejuvenate itself? So the idea here is, I'm going to move to here. So accurate modeling of 3D dynamic ocean currents that determine the plastic fate, and characterization and modeling of the dynamics of marine plastics and all those dynamics, the sinking, the horizontal transfer, the buoyancy of lots of different plastics. So some of the work they've done is just gonna, yeah, okay. Some of the work that they've done is local. So this is Boston Harbor, and using 3D plus time multi-resolution for understanding the dynamics given certain sources. This is all computational, and they are yet to field verify. That's happening now and in the future. Hopefully capturing these models, hopefully are capturing the three-dimensional and especially the internal currents, the deep currents in oceans in different places. What they have found, very preliminary results, what they have found is, so let's take the urban wastewater treatment plant source and urban river source, that those plastics, once they enter into the bay, are pretty quickly just deposited. They're deposited along the coastline. There's probably the majority of the microplastics that you see on beaches, and I say not that you see, actually, you actually don't see these, hard to see. The majority is probably coming from coastal sources with some smattering of materials coming from the immediate bay. So, but probably very little coming from the ocean beyond the bay. And so they're basically beginning to account for those flows. And again, the previous films that I showed really were meant to illustrate the internal waves and the tides and how it affects the plastic flows. Again, the rationale behind supporting this kind of work is, can we get a better sense of the origins of, and essentially the life cycles of these kinds of mega patches, which of course, here they look like islands and they look really dense, but when you're there, it's dispersed plastic. It's super hard to know where they are. There's some very recent work about how these microplastics then travel in extended linear fashion on surface wave currents. And then also to understand, as I mentioned again before, if one were to attack these and try to clean them up as something, what is it, $30, $40 million has now gone towards, can that be done in a way that it's robust? So the coupled strategy of addressing these patches, which are important to address, because the consequences for marine life are just awful. This is the sort of stuff that keeps me up at night, is the effect on us, but also the effect on the extended ecosystem. So hopefully this work will be informing that. Again, one of the measures for us of agency in this work is having the researchers connected to stakeholders and to actual actions in the real world. So Tom is very involved in the law of the sea. And as you know, every country on Earth, I think, except the United States, has signed the law of the sea. So he's acting as a researcher to be able to affect the transposition of that research into policy. Okay, so that's that work. I didn't actually talk about the environmental sensing, but that one I'm hoping that it will launch very, very fast, very soon, I should say. And that is the idea, is there some very fast, economical, effective, robust methodology for tracking, for actually sensing plastics in the water column, in marine sediments, in ocean sediments, in river sediments. And there's some really interesting work here with the nano group in trying to get at that. Okay, I want to talk about a little bit, just a couple more slides, because I have what? How am I doing? 5 minutes, that's good. I want to talk about reuse, recycling, and urban mining. As we know, recycling has collapsed, and hopefully that will not always be the case, and recycling will start up again in a more scientifically founded, economical way. Reuse, absolutely thrilled to have a water bottle. Thank you, JWAFs. It's been fabulous. And I want to say just a word about JWAFs and other groups, Office of Sustainability, I see Susie's back there somewhere, really moving MIT towards reduced plastics use, reduced plastic bottle use, maybe zero plastic bottle use sometime in the future. That would be really fabulous. So I want to, though, say a few words about urban mining. And then I want to say a few words about human health and ecology. And these are more prospective. These are aspirations that we are going to be moving on in the next year. We would love to have partners. Of course, always thinking about JWAFs as well as a partner and others in this project, urban mining, waste to energy, Mighty as a partner. So, okay. So, first topic of urban mining. So I just attended an ARPA-E workshop. And so you may know that there are companies today that are economical, that are doing some incredible work in establishing facilities to take municipal solid waste and to turn it into energy. And the conversion rate is not very good, 40% or so, maybe even less. But the extension of that is towards urban mining, so towards materials, important materials, valuable materials that might actually be mined from the ash of those processes. There's a lot of work to be done to turn that into a sophisticated circular economy, actual material, closed material loop. But I'm actually quite optimistic and very excited about the prospect. Not only because there could be a really, really robust loop, closed material loop that is a buffer when recycling doesn't work, or when recycling is problematic, or when companies continue to produce materials that have multiple layers of materials and recycling, good luck and all that. So I'm offering this rendering just for you to get a sense that there are others who are contributing to this, who are moving along this pathway in a really big way. So you might know Shenzhen is essentially a city-state. I mean, it's Shenzhen, Guangzhou, Hong Kong is, what is it now, 40 million people or so. And this rendering is nice, but the reality is even more impressive. So this is actually under construction. And this is the Shenzhen doesn't know where they're going to go with the volume of, the percentage of material transfer into energy, and then mining the ash for materials. But boy, are they committing big to it. So I think it's a really, really important area for us to think about. And the charge that ARPA-E is giving is, how about a zero emissions waste to energy plant? How can that be done? How can you do it so that there's zero emissions? You might know that there's a waste to energy plant in Alexandria, Virginia, which is a very dense urban context, just next to our nation's capital, that is a waste to energy plant. And it's right in the middle of office buildings and other places. And it's really interesting to me that that kind of process works in that dense urban environment, because Shenzhen is doing this because they have an enormous source, and it's a dense urban environment. So the location of materials to energy, waste to energy, is best done close to, proximate to dense urban contexts. Okay, so that's a few words on that. And on the human health, ecosystem health, ecological health, this is something that we haven't done anything yet, but we are just about to launch with the Center of Environmental Health Sciences here at MIT. So you know, I'm sure, that there isn't today a direct correlation between the ingestion of microplastics and health, either human health or even the health of other species, except for in some very small marine animals, the idea that maybe it gets lodged in their digestive system, in their gut, and creates problems for them. Just simply the scale issue is an issue for them. But for humans, it's not clear. So when you drink water, when you have your salmon steak and you ingest 30 microparticles, is that bad for you? So maybe if those particles have absorbed heavy metals or other synthetic compounds, because those fish are concentrating that material from the ecology in which they live. So that's an open question. And one of the reasons, I'm not naive, one of the reasons why we've gotten really good industry interest in what we're doing is because the prospect of regulation, once that paper comes out and said, you will get cancer from microplastics. Once that paper comes out and is really clear, as clear as can be in the medical sciences, correlation between microplastics and microfibers and human health, there are going to be regulations, and companies want to be at the table to establish those thresholds and to understand, what are the actual solutions that they can begin to affect instead of being caught flat-footed. So we're very excited about this, and again, if anyone's interested in joining us or have some kind of expertise or even just interest, please do, because I think this area is going to take off very quickly, and this is a fantastic group here at MIT. Okay, just want to let you know, we just recently had a workshop at MIT in modeling plastics in the ocean. Aaron Kroll over there of ESI helped to organize it, and it was fabulous. It worked out really well. We're moving ahead with that. But we are in the planning stages of a workshop in the spring. We don't want to leave policy to an afterthought. We don't want to leave it as, once we know the science, let's have a policy workshop. No, this is happening very soon. And again, if you have an interest, please email me and better, both of us, Chris Noble. Chris Noble is our Director of Corporate Engagement, and he's been the steward of this Plastics in the Environment program, and he will be happy to respond to you. Thank you. I guess, am I taking questions? Yeah. Questions?
Hi, I'm Deanna Cohen from Plastic Pollution Coalition. So my question for you is, and I don't know if you know the answer to this, John, but how many projects do you have where you're looking at plastic right now across the board? Yeah.
So funded projects, we have 4. They're modestly, the 2 of them are very modestly funded, and 2 have actual research staff on them they're moving forward. The 2 modestly are more still at the stage of formulating a research agenda. But yeah, and we just added another member to the consortium, so those probably will come, one of those will become real, and we're going to grow from there. So I'm actually pretty optimistic that the 3 areas that I started out with will be funded in short order. Moving into health will probably happen pretty quickly, because that's just a whole nother funding source and set of interested parties that we have not been engaging with. So yeah.
And then for the health component, because I think that's really a key one, is that something that's coming up? It's not part of the...
Yeah, so just to be totally transparent with you, so the relatively new director of CEHS and I have been talking for a couple months now, well, a few months. Recently, we committed, this is an area. They're going to take up this area in partnership with ESI. We're, again, right now, formulating that research agenda. And a key part of my answer is that, hopefully, as you've gotten this message, that we have developed our research agenda with partners, with our industrial partners, with others who are knowledgeable, so Woods Hole Oceanographic Institution and others, and we want to continue doing that. So when we start to launch into the health consequences, we want to be doing this with partners, other partners, to be able to understand, really well the actual problems from the very beginning. And so the last thing I want us to do is step into that charismatic environmental topic mode and just be really happy with the fact that we're doing it and not really getting to the key questions. Mm-hmm. And that's usually discovered with, at the very least, industrial partners.
And you guys are ESI, right?
Yeah.
And is ESI affiliated with any of the projects that are coming out of the Media Lab, or are those
So
separate?
we know of them, they know of us. We're not directly collaborating. Aaron, correct me if I'm wrong, but we're not directly collaborating with them. They know very well what we're doing. Yeah, I'll leave it at that.
Okay. So you're saying MIT's a little siloed?
Well, I think the fair answer is that what we have articulated as a research agenda is not overlapping with what anyone else is doing. Okay. So we're very specifically targeted on those topics that I talked about and have the right people at MIT doing that work.
So we and Plastic Pollution Coalition would be really interested in learning about what you guys are doing and what you guys are doing.
Great.
Okay.
Great. Wonderful. Thank you. Other questions? Must be hungry. I'm hungry too. Great. Thank you.